All right, guys, so in class we were talking about conduction, convection, and radiation. Now, most of these you just have to kind of understand conceptually, right? One of the things that you want to know is that convection by far is the fastest, right? That will transfer heat faster than any of the others. The slowest by far is radiation, all right? And then the conduction is somewhere in the middle. The conduction, however, is one that you're going to need to be able to deal with mathematically, okay? So I'm going to present to you the equation that we will use for heat transfer through conduction, all right? Again, the other two, you just have to understand conceptually how they work. Conduction, we're going to do some math with. So here we go. So up here on the left-hand side, this is your equation for heat conduction, just like that. Now, those variables, this equation is in your formula packet. You can look up the variables in your formula packet. Okay, Q represents the heat and T is the amount of time. So Q over T is how much heat is being transferred for an amount of time, right? Sometimes we refer to that term, that Q over T, as the heat current, all right? Now, not always, but you may hear it that way. And that idea of heat current will be helpful when we start to look at how that heat is being transferred from one place to another through conduction. Now, the A is the cross-sectional area. Even though it's called cross-sectional area, really the area is the total area over which the heat transfer is taking place. All right, the delta T is the change in temperature. L is the length of the rods or wherever the heat is being transferred through. And then K is the heat transfer coefficient. All right, so those are the variables that we're going to use and we're going to talk about. Now, let's see if we can kind of make some sense of each of these before we start throwing into equation. It should make sense, looking at my example down here, it should make sense that if you have a larger temperature gradient, right? So if I've got a high delta T here between my hot and my cold, the bigger the temperature gradient is, the faster the heat's going to transfer. And that should just make sense. If they're close in temperature, the heat doesn't have as much driving force, it won't go as fast. So the bigger the delta T, the more rapidly the heat will go. Now, this is actually an interesting thing here, is that T can be either in Celsius or Kelvin. Now, normally we're really specific and say it's got to be Kelvin. Can you think about why it might be okay to use Celsius here? Hopefully you're thinking about the idea that delta T is the change in the temperature. And the change, for example, if I say I go from 10, that's not a 10, so we're going to go from 15 up to 30 degrees Celsius, then when I find the change, it'll be final minus initial, which would be 30 minus 15, which would be 15 degrees. Now, if I turn both of those into Kelvin, Kelvin would be 15 plus 273, whereas the 30 degrees would be 30 plus 273, and that would turn it into Kelvin for me. Now, when I subtract, I'm going to do the final minus the initial, and the 273s are going to end up canceling out, and I'm still going to get 15 Kelvin. And so what I want you to recognize is that this is one of the few places, because it's the change in the temperature, that you can actually use Celsius. Now, if that makes you nervous, if you don't want to sometimes use Kelvin and sometimes not, it's fine. Go ahead and use Kelvin. There's no problem with that. It'll obviously always work, okay? Now, the L. Let's talk about the L for a minute. Now, look at these rods down here in the bottom. I'm kind of coloring it in there. The longer that is, the slower the heat transfer, the heat current will be. That should kind of make sense, because if it's longer, that means you have a larger distance between your hot and your cold. That allows you to have a slower gradient of temperature as you go across. And like we talked about with the delta T, the bigger delta T actually is a larger driving force. So a longer L will mean that it doesn't go as fast. You can think of this, I mentioned that talking about it as heat current was going to be helpful. You can think of this as electrical current. right? If electrical current is going through a wire, the longer the wire is, the more resistance there's going to be and the more energy you're going to lose. So same thing here. The longer it is, the slower that heat transfer is going to be. All right. The A should kind of make sense. The larger your area is here, the larger the area that heat is going through, then the more heat you're going to be able to transfer. All right. And the K, of course, that's our heat transfer coefficient. That will be different for each material that you use. That will have to be given to you. A higher heat transfer coefficient, look at the fraction, it's on top. Higher heat transfer coefficient means that the heat will go quicker from one side to the other. All right, we talked about that a little bit in class. We talked about the difference between a metal and something organic like wood. We talked about the fact that metals transfer heat much quicker. That's why it will feel colder in the summer and indeed colder in the winter, hotter in the summer. All right, so there you go. That's our introduction. Let's go ahead. I'm going to do one example right now, and then in another video I'll do a couple more. All right, so here we go. We've got a styrofoam box over here. It's used to keep drinks cold at a picnic. Total wall area, including the lid, is 0.80 meters. Now that means all of the surface area, the side, the top, right? All of those areas added together is going to be 0.80. The wall thickness is 2 centimeters. The box is filled with ice and cans of soft drink, keeping the inner surface at 0. And what is the rate of heat flow into the box if the temperature outside is 30 degrees? So a reasonably warm day. All right, so here we go. We're going to use our equation, which is that Q over delta T. The question is asking for the rate of heat flow, so that is the Q over delta T. That is going to be equal to K A delta T over L. So we need the K. The K will be the heat transfer coefficient of styrofoam. Now, that would have to be given to us, or I just went and looked it up in my OpenStax book. The heat transfer coefficient for styrofoam is 0.010 joules per meter seconds degrees Celsius. And I know that's kind of weird units, but the units will work with our area, our length, and our delta temperature in order to give us heat per second. All right, so it'll work out. Don't worry about it too much. So here we go. Let's go ahead and put that in. So 0.010, that is in purely SI units. Now A is the surface area, right? That's the surface area, the cross-sectional area through which it's flowing. In this situation, that's going to be the area of all the sides, because we're saying the heat transfer is happening through all the sides there, which then gives us this area right here of that 0.80 meters squared. All right, it is in meters squared. That's quite nice for us. Then we've got the delta temperature, which we can use Celsius for, remember? So we'll go ahead and we're going to use the outside minus the inside, which is going to give us 30 degrees. And then we divide by the length. Now remember, length is the thickness of wherever the heat is transferring through. So that's going to be the thickness of the wall here. We do want it in SI units. So it gives it to me in 2 centimeters. So I'll write that as 0.02 meters. And I've got all the numbers I need. I should be able to calculate it then. So we type in all those numbers, beep, 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 and we get 12 watts. All right, remember the answer. This Q is heat, so that's energy, that's joules. Time is going to be in seconds, so joules per second. You can leave it as joules per second if you want, but remember that energy over time is power or watts, and so that's the rate of heat flow, is 12 watts. All right, so not too bad. That's a pretty straightforward example. Go ahead and watch the next video. I'll do a couple more examples, hopefully talking you through these ideas. All right?